right, well, as we get started, you'll see that this webinar is co-presented by myself and Catherine Newington from the Australian Computer Society. There she is. We decided not to dedicate slides to our own bios because you can read that in the event description from the booking page for this workshop and in your confirmation emails. But I'm sure you'll hear a little about us as we go along. My background is more secondary teaching, and Catherine's is more primary teaching. So without further ado, we'll get started. Here's the things we're hoping to get through today. Basically, you can see in the agenda there, we spent a little bit of time just introducing the curriculum for those who are brand new to it. Some of you, of course, I can tell are very familiar with it from your names. We'll be looking at the three ways of thinking separately: computational thinking, design thinking, and systems thinking. And then at the end, there'll be a summary and time for some questions. Just one further reminder, you'll see that link to Menti at the top. We'll give you that link again with that code whenever we have an interactive activity to do. Thanks, Catherine. So what is digital technologies? One of the biggest things that we want to get across in this session is that it's not just ICT. It's not just sort of that general capability of ICT, which is really about using and consuming technology safely and effectively. So in the Australian curriculum, ICT is a general capability. In the Victorian curriculum, ICT is sort of explicitly integrated into learning areas like maths and English. It'll mention using ICT. ICT has to do with what you do when you need to use digital technology for doing assignments or doing video editing or things like that. It's not so much about what we create in terms of the curriculum of digital technologies. But on the next slide, what digital technologies actually is a learning area for F to 10, as you'd be aware. It's specific thinking skills like the ones that we're discussing today. It's about creating, coding, working with data, coming up with solutions, and in many ways it's a computer science curriculum. So there's a lot of concepts in there and thinking skills that are used by IT professionals, programmers, engineers, people who work with digital technologies. For more on this kind of distinction, there's quite a lot of resources out there, and we've got some links there. You don't need to go to these now. They will be in the resources doc. But the VCAR have produced these two posters, and there's also a poster produced at the Digital Technologies Hub, which is the Australian curriculum one. And there's also these cards that have been done by the Australian Computing Academy. This is a cool kind of little game you can do, and it's great to do maybe in your staff room with other teachers at your school to really distinguish what are the things that they should be doing that are ICT general capabilities that they should be doing in their own classes, and what are the things that are specific to the digital technologies curriculum. A little bit of a distinction between Australia and Victoria, and one of the lucky things for Victoria is that our content descriptors are not that different from the ones in the Australian curriculum. In fact, they're almost identical. What's different is the way that the curriculum has been structured, and we'll be diving into the Victorian one during this webinar. But the structure of the Victorian one has topical strands, whereas in the Australian one, there's really just a division about knowledge versus processes and skills. So without further ado, there's a little bit.ly link there if you want to follow us, but I'm just going to take over the screen now from Catherine, and we're going to go to that VCAR link, which will take us to a filtered version of the Victorian curriculum. So I'm just going to mute that person. All right, here we go. All right. So in a moment, this should come up for you all. That come up there, Catherine?
Yeah, it is now. It's just loading for me.
Excellent. So this has taken us to the Victorian curriculum webpage from VCAR. And you can see I've taken some filters off, but basically we can see how the curriculum from F to 2 all the way up to 9 and 10, we have these 3 strands: digital systems, data information, and creating digital solutions. And one of the things that Catherine and I wanted to emphasize was how these sort of rows, as we go across from F to 2 up to 9 to 10, they sort of build in complexity and detail and formalization as they go across. Catherine, I think you were did you want to describe the digital systems?
Yeah,
content?
absolutely. So if you start looking at the Victorian curriculum as a continuum, it really helps your development and your skill knowledge around it. And it's not just within the digital technologies curriculum, but it's across the board on all of them. So I want to show you as an example of how it grows, especially for primary school teachers as well. So if we look at the digital systems for the standard and the content descriptor for F to 2, we're looking at software and hardware and the digital kind of components that way. Then when we move up to 3-4, we start to then integrate peripheral devices. So we kind of go from the computer or the system that we have. Then we look at peripheral devices. And then in the 5-6 one, we then start to look at how all of those things are connected and how networks are created. Then we kind of then move on to the 7 and 8 of how that data is transmitted. And then we look at, in the year 9 and 10, is talking about controlling and securing the movement of the data within that network system. So you can see how all of that knowledge continues to grow as our students progress through the curriculum. For primary school teachers, if you start to look at the curriculum this way, it's so much easier for you to get your head around what you're expected to do, especially if you change year levels. So if I'm at a 3-4 level this year and I might move up to a 5-6, don't feel as though it's a whole new curriculum. Use what you've already taught in one year to then move up to the next year, or also moving backwards as well.
Yeah, and I'll give another example. The digital systems, that content descriptor we've just gone through there from F to 2 up to 9 to 10 is a bit of an odd one out because it's a theory one. But if we have a look at, for example, one of the content descriptors from the creating digital solutions strand, we see in the primary that we're starting to talk about sequences of steps and defining problems. But then as we move along, I'll just move across to 7-8. As we move along, we formalize that. We start to talk about decomposing the problem, talking about functional requirements, looking at constraints and scope. And again, that then gets even a little bit more sophisticated at 9-10. So we see that the curriculum kind of formalizes and complexifies as it goes along. I'm going to give you back to the presentation now. So this should come back to Catherine.
Again. There we go.
All right. Oh, this is you. Go for it, Catherine.
Yep. Okay. So this is the little bit of the interactive part that we have. So I want you to go into menti.com and use the code 437621. And this slide should now come up. And we want to ask the question, what way of thinking is most used at your school? And it's a little bit of a rating system. So which one's the first, second, and third? Or even think about which one is most common at your school as well. So
if you're not at a school, you might think of the question as which one is the most sort of familiar to you, or the one that you feel the most confident that you could talk about. Oh, great. We've got ones coming in there. Terrific.
Yeah, beautiful.
I'm not surprised to see systems thinking at the bottom, actually. I was kind of anticipating that.
Yep. See, I love design thinking because it's always, for me, it's always been about creativity. You know?
We'll just wait another, maybe 15 seconds or so. If you are having trouble with Menti and you can't get on this time around, we will have some more activities later. So yeah, that's a good point, Daryl. Design thinking is also common to design and technologies, which is the subject that incorporates woodwork, metalwork, textiles, food.
We'll keep going on now.
Yeah.
Yep. Beautiful. Okay, so computational thinking is one of the 3 ways of thinking, of course. And when we're talking about computational thinking, we're looking at the steps from making algorithmic solutions to a problem. So we're really coming up with how a solution that a computer can carry out. So within computational thinking, we actually have 4 other styles of thinking. And I always really quite struggled to get my head around each of these different types of thinking. But I'm going to take you through them, and I'm going to take you through an analogy of completing a puzzle to help you understand the different types of thinking. So when we're looking at decomposition, we're looking at breaking down a complex problem into smaller manageable parts. So the related vocab that we've got there is deconstruct, reimagine, divide. And when think of a puzzle that we do is that, and I've been doing a lot of puzzles while I've been at home as well, is that when we want to start completing the puzzle, we almost mentally take a list of different smaller jobs that we need to do when we're working on that puzzle. So we might start in a particular corner that has the same colours. We might be looking for a style or a theme that we're going for as well. So when we're looking at composition, we're breaking down the problem into smaller manageable parts. So then pattern recognition is that when we're looking for reoccurring themes, similarities, or leads that will then lead to predictions or shortcuts. So the related vocab that we're looking around pattern recognition is group, identify, name, sort. So think of, again, that puzzle analogy is that when we're completing that puzzle, we're always looking for different styles that might fit. We've got that big, we've got that tray of pieces of puzzle, and then we're going to be finding those other ones. Just like I said before, that if you're working on a puzzle and you're looking for a particular colour, that's then the pattern recognition that you're going to be looking for. It may also be a style of puzzle that you're looking to fit and the rest of the puzzle together as well. Then we're looking at abstraction. And this is when we're focusing on the important information only and then ignoring everything else. So then it might be we're looking at representing, refocus, generalize, decomplexify, and bringing up that analogy of the puzzle. When I always think about abstraction is when we start a puzzle, the first thing that we always tend to do, or this is the first kind of step that I use to complete a puzzle, is that I always look for the borders part. So what I'm looking for is or only the pieces that have the flat edges. So I kind of ignore all the other colours, the pieces and everything else, and just focus on finding the bits with the flat edges. And then, of course, when we come across that corner bit, then that's when we get really excited about it. Then we've got algorithmic design, and that's when we're putting into the step-by-step solution and really breaking it down and creating the steps and rules to follow to solve that problem. So then that kind of, the algorithmic design brings in a sequence of steps. And when we're looking at sequence of steps, we're looking at explicit steps as well. That's when our coding comes into it. And that's where we might also have flowcharts as well. So right before, I want you to think, when you open up that box with all those puzzle pieces, you start to almost think about the process that you're going to take in order to complete and solve that puzzle. I want you to think about what actions we have when we might find a puzzle, or when we repeat it as well. What happens when we pick up a piece of puzzle that's not right, we put it down. So all of those little actions are part of that algorithmic design. So here I've got a couple of examples, and these are unplugged activities that I've used within some schools, where it's showing those sequence of steps through flowcharts. So as you can see, we've got one which is how to make butter. Now, it might be a little bit small for you to see, but I want you to see just and focus on the overall look of the flowcharts. So how to make butter, that's the first one. That was presented for a foundation to 2 class. So it was the perfect opportunity when they were looking at food and fibre and where things come from. We were then able to bring in the style of a flowchart, and you can see that it's just that sequence of steps that go through it as well. Then we were using flowcharts another time when it was a great idea from a teacher, when we're looking right at the beginning of the year, when we're kind of creating rules within our classroom. And then we created, instead of creating a poster or a set of rules, we presented those as flowcharts. So you can see that the middle one was presented for grade 3-4 classroom, and you'll notice that there's some blue and then there's some red ones as well. What I wanted to visualize for the students was the red were the ones that had the branching, so they came off. So you can see the very first one, it branches off to a cross or a tick. So we also used some visual aids as well and some pictures in there too. Then I was thinking, how could we present flowcharts to something that our grade 5-6s know? And I'm pretty sure you'd all agree that everyone knows how to create a chatterbox. But what we wanted to do is unpack how we use the chatterbox. And so you can see that there is on that one was for a grade 5-6 class to teach them about algorithms as well. So it starts off with picking the colour, what happens when you pick the colour as well, then it branches off, and then there would have been a repeat within that, because I know when you do the chatterbox, you kind of do the numbers twice. So it's perfect to add in that repetition for the students as well.
I have to unmute myself. Apologies, everyone. For the secondary years, I want to give the example. This is a typical kind of coding challenge, is to do a number guessing game. In this case, we're developing an algorithm for a number guessing game. The computer is trying to guess your number between 1 and 100. So you think of a number, the computer is going to try and guess it. So that's the program we're going to try and make. As far as computational thinking goes, some of the things we might do here is we might start by making notes. So decompose, start to think about how we can break down this problem, because there's quite a few things going on when we think about it. We do a flowchart or pseudocode to plan out our algorithm, to look for the patterns and also to generalize if necessary. And then we code. So we use a general purpose language. In the case of the secondary years, this example ends up being done in Python. So you can see here, my notes are on the left. Here's what I think needs to happen. The user needs to think of a number between 1 and 100. The computer is going to take a guess. The user will type lower or higher. I will just keep the left for now. The computer keeps guessing until it gets the right number. And we might ask ourselves, what does the computer need to keep in memory? And this algorithm is, if you want to explain it, this algorithm is a binary search. What's happening is that the computer is going to keep guessing halfway, and that's what a human being would try to do. I don't want to go too much into all the detail of that, but let's start on the pseudocode. So we start by displaying think of a number, and then we set 2 things. And these are the things we've decided that the computer needs to remember. It needs to remember some kind of bottom boundary for where the lowest number that's in the current range, and a top boundary, which in this case is 100. So if I was playing this with the computer would start saying, well, I know it's between 0 and 100, so I might start with 50. Thanks, Catherine. So then we put in a loop. So this is an example of looking for a place that we can see a pattern. Something needs to happen over and over and over. With pattern recognition, and we've put in a loop here. This loop, I've simplified this by saying to repeat forever. In this case, the loop's just going to go on forever, but the first guess the computer makes will be the average of bottom and top, in this case 50. And the computer's going to display, is it 50? And then we ask the user for their response, and we give the user a choice of saying lower or higher. And then this is where the sort of clever bit happens. If the user says lower, then we set the new top boundary. In other words, the computer knows that it must be now less than 50, so it sets the top to 50. Otherwise, if it was higher than 50, it would set the bottom boundary to 50. And then we repeat. So what you've seen here is pseudocode, which is kind of like a universal false code. It's not a particular language. It's not JavaScript. It's not Python. But it is something that is part of the curriculum. In the year 9-10, we see it written as they have to express their algorithms diagrammatically, so maybe with a flowchart, and in structured English. And in this case, we're using pseudocode as our structured English. On the next slide, this is what the final program might look like. I did this up in REPL, which is an online thing for doing Python programs and other languages. But basically, you can see that a lot more has happened as we've done the coding. The program ends up looking a little bit more complicated, and that's because when we started doing the coding, other things came up. We have to do this floor business because we realized that it was giving us 50.5 or 25.75 or things like that, and we have to start, flooring it out or rounding it to the whole number. And these are all things we discover as we start doing the code. But isn't it good that we did that design first, so that when we get to the code, there's less of that stuff to have to worry about, and we can think more about the implementation.
Can everyone hear me? Do you just want to pop in the chat? Because we may have, okay, fantastic. All right, so we've lost Nathan. I'll continue going on with my bits. And then as soon as we know that Nathan is back in again, we'll bring it back to anything that he's missed. That's awesome. That's so good. At least we've got someone here. All right, so we'll talk about this part a little bit later. So we'll get Nathan to bring that part back again as well. What we're also going to have for you in the chat is that there are so many resources out there, and it was really difficult for us to think about what would be the really great resources for us to provide you when we are looking at the 3 ways of thinking and the computational thinking. So what we will put in the chat to you is a bit of a Google Doc that we have with all of these other areas as well. So I just want you, if you want to, just quickly before we move on, just pop something, just look at the bit.ly as well. So there's even more resources out there for you to use as well.
I am so sorry about that. My internet at home dropped out. I'm back.
Beautiful.
I happen to have a mobile router that I could switch over to. So I'm sorry about that, everybody.
See you back again, Nathan.
We'll carry on. I'll let Catherine carry on.
Okay, so what I want you now to use is, if you haven't got onto Menti, what is your key takeaway for computational thinking? And so this is just, we're going to create a word cloud together. So any words that pop in when we're thinking about computational thinking. And don't be shy with this either. It's really great to have something when we're going to be doing something collaborative. Now, you don't have to put all 10 in as well. You can put in a couple and then press enter, and then we've given you the opportunity to press submit a couple of times as well. Oh, this is looking fantastic. Love to see you guys playing along as well. Process is a big one.
Yeah, it gets a little hard to read as it gets more words into it.
Yeah, that's great though.
I think we can capture it for later if anyone's keen. I think we might be able to capture it.
So we can provide you with all of these results and stuff as well. Oh, there's a tiny little word. I can't read that one. That's great.
Yeah, on the green. We'll have to do it on white next time, but yeah.
Yeah.
Cool.
Some smaller ones there. Fantastic. Oh, I think we've finished off. Oh, no, are we still going? Unplugged, yeah, that's one for me that always comes out as well, that we can do unplugged activities. That computational, especially for primary school, is don't put that added pressure on you to do something with that's digital as well and coding as well. If you're not too comfortable with that, start off small and start off with some unplugged activities. It'll then get your confidence up, and then you can slowly move on to using visual programming. Testing, yeah, absolutely. Fail, yeah, I've done that many times when I was coding. I remember in high school I was doing some coding and my whole program wouldn't work because I put the difference between a colon and semicolon, and that happened to me when I was in year 11, and I still remember it to this very day. I was racking my brains for hours trying to work out what was going on, and it was the difference between a colon and a semicolon. Oh. Nathan, are you ready to move on now?
Yeah, I'm set.
We're still moving along. Thanks again for everyone for participating in this as well.
All right, design thinking. So really design thinking is, I've noted here that it's broader in scope in a way than computational thinking. It's kind of an overarching methodology or approach towards almost any problem or opportunity. We've defined it here as employing a creative process to understand a problem or opportunity and then to imagine and design a solution. And as we noted before, it's also a big part of the other technologies area, which is design and tech, which includes your food and your wood and all of that stuff.
Yeah, and especially in the primary school area, it takes you through that process of thinking as well that you can adapt. So when I've been doing any of the design thinking parts of it, I almost automatically go over to the design and technologies curriculum, and I almost do a little bit of a one-for-one. And so it's a great, to be able to mark against two curriculums almost simultaneously makes my life writing reports a lot easier. So one style of design thinking process that has been used quite a lot in primary schools is the Stanford School design thinking process. So I'm going to take you through this now and talk about the different types of steps that they have between all of these ones. So when we look at empathize, when we start off, is that we kind of develop an understanding of the challenges and think about who might be part of that challenge as well. So it's almost a step into that person's shoes and think about who they are and what type of problem that they might have within society. So one of the key questions that you might want to ask at this stage is, who is my target audience? And also, what might they be feeling, or why are they my target audience as well? Then when we move to define, is that we're looking clearly at the problem that you want to solve. And so then you might ask yourself, or ask the students, what problem am I actually solving? Then as you move on to it, and this is one of my favorite parts, is that you start brainstorming potential solutions that you've developed. So how many different solutions can I come up with, and which one then is the best one that I can pick? The ways that I've done this before is at a whole class level, we're all together and we do a quick brainstorm with each other. Then I get the students to work into a smaller group, they brainstorm again, and by that stage, they may have then been able to identify their own idea and a solution that they want to put in as well. Another little handy thing to do is have 4 or 5 different big butcher's paper around the room and get students into different groups, and then they go around to each of those butcher's paper. They've got 10 minutes, or actually 2 minutes, to write as much as they can, and then they move around the different butcher's papers. So you've actually got all of these ideas within about 10 minutes of a class, because we really want to support the students, especially at that idea and solution stage. Then we go into prototyping as well. And so we think about what that actual solution might look like. And when we are prototyping at a primary school level, we're looking at just really even a good old-fashioned pen and paper as well, and get them to be drawing and to start visualizing what that solution might look like. So then it will be a case of what materials can I use to create this prototype. So you might do a 3D model, or you might just do a 2D model. And then, of course, testing it as well. And so looking at that cycle of, well, what have I done and how can I improve, or is there anything that I've missed out on? One activity that I have done with a primary school is I supported a primary school out in Mill Park. And the teachers were already doing an activity. So their unit of work was all just focused on healthy unit. I then came in, and you can certainly see the correlation between staying healthy and also digital technologies and how we use digital technologies. When I was talking to the teachers, I think every single one of them was either wearing a Fitbit or an iPad watch. And I'm like, already you've got a system on your hand, on your wrist, that is taking data from you. So they started then that design process. So instead of just being at that normal level where we look at how to stay healthy, we introduced the digital technologies curriculum by asking the students to create and design an app that would help them stay healthy based on one of those ways that they had found and identified previously. And what I love about design thinking, and I'm just so passionate about this part, is that as soon as you bring this in, you start to have student-driven projects. So the challenge in the project that we gave them was just create an app of how you can stay healthy. It didn't really matter what was in it, but all the students took the same process, the design process, to get to an end product. They didn't do any the actual visual programming side of the app because the teachers weren't comfortable with that. However, we did a lot of other stuff as well. And what I loved is the type of apps that we had was really to the individual student. So we had one app where it was a mental health app because that student had actually been involved in a lot of bullying at school. And so she wanted to create an app that would support fellow students if at any time that they were going to be bullied. Another boy in the classroom absolutely loved running and sprinting, and he wanted to create an app that would help him sprint a little bit faster. So here's a couple of photos to the right that I have of the design process that we used with the students as well. So you can see that we created a little bit of a booklet. And so we talked about the hardware and the software, and it's all about unpacking that problem. And then you can see on the top one, it looks a little bit like a flow chart. And that was them starting off that design process and thinking about the type of things that they would need to have in their app and how they were connected with each other. One thing that I absolutely loved about this is I was in the classroom when they were doing this and also the teachers didn't feel comfortable doing this over a couple of days. They ended up implementing it as a one-day event. So it was almost a bit of an incursion where all they did for the whole day was spent the whole day of that whole design process. And by the end of the day, majority of the students they'd almost finished the digital technologies part of that curriculum. The teachers weren't confident for doing it over a certain amount of days, and that worked well for them. I was chatting to some of the boys at one of the table, and the two pieces of feedback that I can remember was one of them said, I love sketching and I'm now able to sketch. So they even drew some pictures of what some of their screens would look like on their app. And the second one, and that really blew my mind, is that he was a huge coder, but he thought that he had outgrown Scratch. And he said to me, I now can find new ways and new things to put into Scratch. So already these students, we were already targeting different things that the students and the needs and the interests of these students, but especially that student who we weren't touching the coding. He knew how to code, but he was going to take that home and do it as a little side project. And I mean, I think we certainly hit the mark when it comes to digital technologies and engaging our students, because when we've got someone who's voluntarily almost doing homework, we know that we're doing a pretty good job with our students.
This part here is for secondary teachers. We have another problem-solving methodology that I wanted to go through, and this one is also used within Victoria's VCE Year 11 and 12 applied computing. But just before that, I saw a question just now, or something someone put in about the difference between design thinking and a design process. And you'll notice that we are mentioning a lot of processes here, and there'll be a couple more as well. The Stanford Design School is one of them. This is one of them. There's others. Design thinking is often collapsed in with a design thinking process, or design thinking skills are grouped underneath the various stages of a design thinking process. But there are specific skills, and some of the resources in the document that we've linked, particularly the one from Stanford Design D, actually talk about some of those in detail. We will also go into one of them in an activity in a moment. So yeah, this problem-solving methodology divides it into 4 stages: analyze, design, develop, and evaluate. But again, the design part in the middle there, we often consider that part of the whole process. So we might just skip through to when this is complete rather than take you through every bit. So you can see on the left there, overarching it all is the planning or the project management aspect. But we see that the 4 steps here, in the analyze step, our focus is on the problem or the opportunity or the need. So what is it? How do we understand it better? What are the goals and scope of the solution that we actually want to come up with to this problem? And who's the audience? What environment does it have to work in? Those sorts of things. In the design stage of this methodology, we're asking more about what does the solution look like? How will it work? How will it be used? And also we're setting criteria for how will I know that that solution actually did solve the problem or need. In the develop stage, that's when we actually do it. So you could say that's when we're doing the making, doing the coding. But it's important to emphasize, and I'm sure Catherine would agree with the other methodology as well, that these don't necessarily have to be done always in this order, that you do sometimes jump around. So for example, we might have a go at a bit of coding so that we can get an idea of what's possible and what's not, and things like that. And then of course the evaluate stage, that's where we look back at our criteria that we came up with in the design stage and we say, did it actually work? Did it solve the problem or need? And we also, particularly in the F to 10 curriculum, we look at the impacts, environmental impacts, social impacts of the technology. I wanted to dip one more time, and I'll just bring that up. I wanted to dip one more time into our Victorian F to 10 curriculum, just to show you. So how this is embedded in, and it's really there in a lot of detail. But if we look again at this creating digital solutions strand with these content descriptors, and I'm going to go across to the 7 and 8, because I'm a bit more familiar with that. But we're starting to see those steps that we talked about actually from top to bottom here. So you'll see at the top, defining and decomposing the problem. Then we've got designing the user experience and designing the algorithm. So 2 aspects of design. Then we've got develop or implement. And then lastly, we've got evaluate. So you're starting to see that sequence being embedded already into that strand in the curriculum. I'll go back to the presentation now. Is that coming? Oh, there we go.
Yep, we're all good. We're back again.
The other thing I wanted to show you is just an example of a physical tech project with the BBC Microbit. BBC Microbit, some of you are probably aware of it, is a little device that's become quite popular in schools. It's sort of, I guess, a more classroom-friendly alternative to something like Arduino. It's a tiny microprocessor, and you can program it, and you can set it to do lots of different things, and then there's all sorts of add-ons as well. I wanted to show you this. Actually, I'll give you the link for it. Again, we'll provide the slideshow later, but it takes you through sort of an example project and goes through all those stages for a group of students. And what they're doing is they're using the BBC Microbit to make a thing that gets attached to your locker. And it's to solve the problem of too many students hanging around in the locker bay and cluttering up the locker bay. So the microbit goes there and you set a timer so that when the person goes to use the locker, they press a button and then it times out when they've finished. They need to get off their locker and go away so that other people can access their lockers. So it's kind of like a little real world school problem that they try to solve with that technology. Okay, so we've got another activity now. So if you go back to where you've got your Menti, it should come up for you with this next activity. And I'll just do a little explanation of what this activity is about. So a how might we question, and this is given again in that Stanford Design D, one of their guides. A how might we question is a question that's used to help us do ideation. It's used to help us do brainstorming. And what we have here is basically a how might we question would be something that is broad enough to include a range of solutions so that the brainstorming can really cover a lot of different possibilities, but not so broad, not so broad that it's just too vague and, there's no helpful boundaries. The example we would sometimes give, and that's given in the document, is a how might we redesign ice cream to be more portable? So maybe we're running an ice cream shop and we want to make it easier to carry your ice cream around. Now, if we said, how might we create an ice cream cone that doesn't drip, that might be a bit too specific. If we were to put that as the start of our brainstorming session, we might find it a bit too narrow. We're not exploring enough. But if we said, how might we redesign dessert, then that might be too broad. There's too much in that. We're not really giving any helpful boundaries. So you can see 2 points of view in our challenge here. Jim is tired of tidying away Lego that his daughter Patty constantly leaves on the floor. And Patty's point of view, Patty is frustrated that her dad keeps dumping all her Lego bricks in one big box. So in this one, what we're looking for is a how might we question. So I can see someone's posted sort of a solution or one option there, but we're looking for the question that we might put to get started in our brainstorming. So how might we what? See what you can come up with. We've got a couple coming in. We'll give you guys a bit more time, especially if you're typing on your phone, because it takes a bit longer to write things out. And we don't want anyone getting autocorrected. That's a good question. Let's assume it's her bedroom. It's not a shared area. Oh, some good ones coming in here. What do you think, Catherine?
Yeah. There was one about, I like how might we store the Lego so it's easier to manage. Absolutely.
Yeah, because that's not too broad. It's not like, everything, but it's also not too narrow. It's not restricting the possible brainstorming.
I like the one that it says, how might we keep Lego off the floor when it's not being used? I think if someone was able to solve that problem, they'd probably up for a Nobel Prize.
That'd be awesome.
Imagine all the parents in the world that would never have to worry about stepping on another piece of Lego again.
So we might just set a timer to wrap up this activity, because we don't want to keep you guys after this. So just 1 more minute.
Yeah.
You could use a microbit counter. So just to reiterate, remember that a how might we question is the question that prompts a discussion. So it's designed to be the beginning of a brainstorming session, but not necessarily all the things that might come up in a brainstorming session. All right.
Beautiful. So I think we can't do any more. There's some really great suggestions on that one, Nathan.
Yeah, awesome.
We'll keep trudging along.
Yeah. This is where I got this from. So again, we link to this resource in the resource document. So feel free to have a look through that. It's just one thinking skill, one design thinking skill as part of a process. There's the link to the document again, in case you missed it the first time. It's worth considering a couple of other design methodologies that often get talked about. One is the British Design Council's Double Diamond, which is all about thinking about how we expand and then focus in, expand, focus in. That's that double diamond approach. It's worth Googling and having a look for. Another one is IDEO's human-centered design approach, which often gets mentioned too, so it's worth having a look at that one as well. We're getting on to our last thinking skill now, which you probably guessed what it is. What we want you to do, this is one more activity on Menti, and what we'd like you to do is think about the functions and just list, if you see one that already appears that you were going to say, try and think of another one. But we're thinking of the functions your smartphone can do. So for example, it can help me with a map, or it can play a video. So have a go, see what you can suggest. Yeah, tell time. Yeah, don't always think of that one. I think that was tell me the weather, isn't it?
Yeah.
Seem to have lost 2 of our columns.
Yeah, I don't know what happened there.
Sorry about that, folks. If you might not be seeing all of these, that was unexpected.
That was.
Tell me if I'm in tune. Yeah, I've seen those tuning apps. Yeah.
Oh, yeah, wow. Yeah. Alarm clock as well, absolutely.
Again, sorry if yours isn't coming up here. There should be 3 columns on the screen, but that's okay. Connect with others. I can see some people have put in multiple suggestions. Predict text. Find directions. Okay. I know you probably got more, but obviously there's a lot, isn't there? Smartphones are one of those things that do a lot of different things. So on the next slide, the next question we've got for you is, now, what are the hardware and software bits in the smartphone that make that happen? I saw someone suggest the gyrometer or things like that. What are the other maybe input devices, output devices, the parts of the smartphone that actually let you do those things? Speaker, yeah.
Lens, yep. I was thinking of lens, GPS, yep.
Microphone.
Yep.
Touch screen, that's the one of the big ones, isn't it?
Mm. If students ever give you, like, take a photo and get them to unpack a little bit further, go, well, what do you need to take a photo as well?
Mm. The other thing is,
unpack it even more. Because, you know, something like the top one where we've got make a phone call, well, what do you need to have in order to make that phone call? So it helps them really unpack the hardware and software components just that little bit further down.
And if you're doing with this with your students, you might first get them to draw a picture of their phone, like on paper, and then annotate it as if they were annotating a diagram with the different things that it does. Cool. All right. I think that was the last activity. So obviously, we're pointing a little bit to something called systems thinking here. And systems thinking is often one of the ones, and you saw when we did the poll at the start, that it's often the one that's least talked about. You know, people sort of aren't sure exactly what it is sometimes. I've defined it here as big picture thinking. It's looking at connections and dependencies within a system and also between systems. So you can see behind there is a bit of a metaphor of a food web or an ecological web. And we kind of talk about this. Kids are often familiar with this idea that if we took the clownfish out of this system, then it would have impacts on the other things in the system, possibly quite catastrophic impacts. And it's the same with information systems and computer systems, whether that is just purely software or whether people are involved, and people are always involved somehow with a computer system. But these connections and dependencies really matter, and they will affect things. Some examples of systems thinking problems, and this is one that we often talk about in senior secondary, which is if you're bringing in a new system at your school, maybe a new learning platform that your kids are supposed to use, or a new system for tracking when kids go to excursions or camps or whatever, the IT team at your school has to do a lot of work usually to make this work because you've got systems already for the student accounts, so you have to integrate those. There's whether it'll work on the computers at the school and the hardware, and the parents need to use it. And what about security of all that student data? So all these things come in. We already talked about the ecology one. Oh, Sandra says the de Bono hat. Yeah, I think the de Bono hats, you know, the blue hat and the red hat, that's a definite way of analyzing systems thinking problems. Climate change science, the atmosphere is a very complex system. There's lots of feedback loops that we don't fully understand. I was thinking of COVID-19, and just the way we were talking about how, you know, like we as teachers are seeing largely one part of this whole system. We're seeing what's going on with education, but then what's going on with medicine, what's going on with, you know, this workplace, that industry, you know, health, you know, poverty, all these different aspects, and they all have effects on each other. This is a great little quote, I think, that really touches on systems thinking. You think because you understand one that you must therefore understand two, because one and one make two, but you forget that you must also understand and that's the key thing. It's the and is what makes systems thinking. So what are the kinds of skills that we have with systems thinking? Maybe, I think we've got something on the next slide. Yeah, we've got some links to resources there because we are running out of time. There's some great habits of mind, and this comes from a pack that's freely available by the Institute of Play, where we look at habits of mind that encourage systems thinking. So recognizing, for example, recognizing how system structure causes its behavior, identifying, someone mentioned before, cause and effect, assumptions and unintended consequences. These are some of the big things that happen with big systems. And that's actually the end of our main presentation. We've got 5 minutes to spare, so that's awesome. We would, yeah, appreciate any questions that you wanted to ask at this point. I see one there from Paula. Is something a collection or a system? And that could be a good question to ask when you're dealing with a systems thinking problem. A collection is, they're still operating, these things are still together, they just happen to be together. Whereas a system is unable to continue doing its function properly if something is removed. Thanks for that link, Jane. That's great. Waters Centre for Systems Thinking. Catherine Kirsty asks, I struggle with systems thinking in the primary environment. Any suggestions?
Kirsty, what grade level is it? Just to kind of get a little bit more of a context. The Digitech specialist, yeah. So anytime that I've worked with and supported some Digitech specialists, is that we've kind of gone from what I have found that has worked really well is looking at that design thinking, and part of the design thinking that they do when they are, you know, creating something like the app is then bringing in the systems thinking into it, and what things do they need for their app to function or something else. Another really good systems thinking one, especially in primary school, this works out really well. Look at bike ed. So when they might be completing bike ed at that time, look at the system of a bicycle. And then what I really love them to do is that they unpack that bicycle, but get them to redesign a bicycle as well, bringing in some digital technology stuff as well. So hopefully that might help you with a couple of ideas.